Hi everyone, in this video we will come back on my formula to calculate the circumference of an ellipse, and this time I will give you applications, numbers and analysis as you have asked me. So first let's start by reminding the formula. I have stated that the circumference C of an ellipse with a semi-major axis A and a semi-minor axis B is equal to 4 times pi over 2 to the power of B over A times A. And if you want to remember, or if you want to know how you obtain such formula, I invite you to watch the video on how to calculate the circumference of an ellipse that I did in the link here above. Okay, so let's move. So first I would like to review the process that I went through in order to calculate the circumference of an ellipse. So basically here's what I did. I took a circle with a radius A on a y plane with the x-axis passing through the center of the circle. And I said that if we observe, or if you look at the circle from z-axis, which is passing through the center of the circle, and then we rotate this y plane with an angle theta, well, we obtain an ellipse with a semi-major axis A and a semi-minor axis B. And I had that some of you told me that this needs to be proven, okay, that I need to demonstrate that rotating a circle or tilting a circle becomes an ellipse. Well, I did another video where I demonstrate this, and if you want you can watch it here in the link above. Okay, so let's continue on this one. Just quickly as a remark, this length B is actually the distance between the x-axis and the height reached by the circle after rotating it with the angle theta. And so if you want to know the distance of B, well, if you translate here the segment B on A on the old y-axis, well, you see that the ratio between B and A is cosine theta, so B is equal to A times cosine theta. Okay. So with this statement, I would like to give you two applications very quickly. It's going to take me like 30 to 40 seconds, and then I will give you numbers and analysis. Okay. So the first application is the eccentricity with the method of rotation. So remember, the eccentricity can be calculated by doing the square root of 1 minus b over a squared. And remember that b is equal to a times cosine theta, so we can rewrite this as b over a is equal to cosine theta. So I'm going to replace b over a by cosine theta, and this gives me square root of 1 minus cosine square of theta. And if you remember in trigonometry, when you do the cosine square of an angle plus the sine square of that angle, the result is 1. So if I do 1 minus cosine square of theta, this gives me sinus square of theta. So I'm going to take this result and inject it in my eccentricity equation. And this gives me eccentricity is equal to square root of sinus square of theta. And square root and square, they cancel each other, and this gives me eccentricity E equal to sinus theta. So here is how you can calculate now the eccentricity simply by knowing the angle of rotation. So if I take a circle and rotate it with an angle theta, you obtain an ellipse, and the eccentricity is equal to sinus theta. And if you don't rotate it at all, you keep the angle 0 degrees, you keep it a circle, so sinus 0 degrees gives me 0. So as you can see, the eccentricity of a circle remains 0. Okay, the other application that I would like to show you is the area. If, for example, now I want to calculate the area of this circle C, we can call it AC, the area of the circle C with radius A. This is equal to pi times A square. And if I want to calculate now the area of this ellipse, we can call it AE, the area of the ellipse E with a semi-major axis A and a semi-minor axis B. This is equal to pi times A times B. But remember again that B is equal to A times cosine theta. So I'm going to replace here B by A times cosine theta, and this gives me pi times A times cosine theta. We have 2 times A here, so this becomes pi times A squared times cosine theta. And here, if you recognize it, P times A square it's actually the area of the circle C. So we can rewrite this as the area of the ellipse AE is equal to the area of the circle AC times cosine theta. So here is the second application I wanted to show you. So if you take a circle of area AC and rotate it with an angle theta, it becomes an ellipse with the area AE such as AE equal to the area of the circle AC times cosine theta. That's all for the application. Now let's look at the numbers. So here is what I'm going to show you now. Basically, I took my formula to calculate the circumference of an ellipse, and I took an ellipse with a semi-major axis 1, and I varied the semi-minor axes such as we have the ratio between the semi-minor axis and the semi-major axis starting from 0. So 0 in this case it's what I call a flat ellipse, so with the semi-minor axis equal to 0. A flat ellipse doesn't really exist, okay? It's just me, I'm using it for my demonstration, but it's just a concept, okay? So from a flat ellipse where b over a is equal to 0 until a circular ellipse, so a circle, where b over a is equal to 1, so b is equal, the semi-minor axis, b is equal to the semi-major axis a, so it's a circle. And this is the result that I had by doing those calculations. So as you can see, my circumference started from 4 times a until a circle that of circumference 2 pi a, okay? So as you can see, it's pretty linear. And then what I did, I took my results and I compared them with the result from this integral to calculate the circumference of an ellipse. And when we compare them, you can see that indeed my results are not the same results as this integral. Well, I still have a small error margin. I mean, I'm not like 1,000 miles away from it, but still there is an error margin. So how I calculated this error margin? I simply took my results, divided them by the results of the integral. That gave me naturally a factor. I did -1, and then I multiplied it by 100 to have it in percent. And I projected those results on the same graph. And so here is my error margin graph. And so as you can see that first my error margin is very small, okay, and then it starts to increase. So it's 0 at the beginning and then it increases to a maximum around b over a equal approximately to 0.28, and this error margin reaches a peak of 4.44% approximately, and then it decreases again toward 0%. And here I did something. What I wanted to do is I just focused on the error margin curve. And here I noticed something. I said, well, wait. I saw this curve somewhere. I just remember I saw it somewhere. I don't remember where, but I saw it somewhere. And then I remembered where I saw it, and I remember how to get it. Okay, so let's have a look to this curve. So it's f of x equal to x squared times 1 minus x squared, and we close everything up. And here is the curve I was talking about. As you can see, it looks very, very, very close to my error margin curve. And I know that that's not how we work in math. I know that it doesn't matter, you know, that it's close or not close, but they look almost the same shape, okay? So this is the part of my work that I kept for myself, and I didn't want to share because I'm not very happy with it, and I don't want to share inaccurate stuff. But I took time to play with this curve and to adjust it to my error margin curve. So here's what I did. In my error margin curve, the x here starts from 0 and ends at 1. This one starts from -1 and ends at 0. So I need to shift everything to the right to make at least my this x-axis matching my x-axis. So what I did, I just took x up and I replaced it by x minus 1. So here we replace everything x by x minus 1 up, and here is it. So now here is the result. And I hope that you understood that here the x-axis represents, in my case, b over a. So what we can see that here the top of the curve, so the peak of the curve, is reached at when a is equal, when a over b is equal to 0.29292929, which is 29 over 99. And in my case, the peak is reached at when b over a is equal to 0.28. And it's not exactly 0.28, it's approximately 0.28. And I said, okay, you know what? I know that's not how we work in math, and again, this is why I didn't want to share this spaghetti work with you, but I'm showing you what I did, okay? Because I had a lot of fun with it. So I said, okay, 0.292929 is not very far from 0.28. It's okay, let's keep it. And something interesting here, what I can do is I can change the amplitude of the curve simply by putting a factor. Okay, so if I put 2 here, for example, you see, now we still have the same peak as 0.292929, but simply the peak is now at 0.25 on the y-axis instead of 0.25 like the previous one. So here is what I want. I want the peak to be reached, okay, so I want the maximum of this curve to be reached at my maximum error margin. I want it to be reached at 4.444%. So let's solve this. So this is our function. Again, just remind that x, in this case, it's b over a, but we just keep it x for now. And we saw that for f of 0.292929, this gives me 0.25. Let's just rewrite this with friendly numbers. This gives me f of 29 over 99 is equal to 1/4. And I don't really know if 29 over 99 is really a friendly number, but anyway. Remember, the peak is reached at x of 29 over 99. Okay, and when the peak is reached, the result is 1/4. And I want to find a factor that doesn't give me 1/4, but it gives me 4.444, which is 40.9, 40 over 9. Sorry. Okay, so we saw that you can just multiply the result, and this will simply change the amplitude of the curve. So it's not complicated. We just multiply 1/4 by a factor to have 40 over 9. And this factor n is equal to 160 over 9. At the beginning, I tried to see if this number really represents something. Well, we can write it as 4 over 3 square times 10, but honestly, no, I mean, it doesn't represent anything. I mean, this number has no significance, and the second way to write it, 4 over 3 squared times 10, is completely irrelevant. So we will just keep it as 160 over 9. So here is now the function of b over a multiplied by 160 over 9 to give me 4.444 when b over a is 0.29292929. Okay. And so if I draw this function now, as you can see, it is not the curve from 0 to 1, it is not exactly the error margin curve that I had before, but it's almost the same, if you can say almost the same. I know that's not how we work in math. I know we don't work with almost the same or it's almost this. I know, but at this stage, I don't have much clue, you know, to move forward. So I'm just trying to move as I can. Okay, I'm taking the tools that I have around me, and I try to progress as much as I can. So I tried to progress with this. Said, okay, you know what? Let's say that this curve is almost equal to the error margin curve, and now I have a method to calculate my error margin. Okay, so I don't need to take values and just look on a table and project this on a graph. I can calculate it. So now that I can calculate it, well, I'm going to apply it to my formula to minimize to the maximum my error margin. So here's what I did. Remember, previously to calculate the error margin, I took my result divided by those results minus 1 times 100 to have it in percent. So then here's what I did. I took the new calculated error margin, I divided by 100 because that was expressed in percent, and I added 1. I just did the opposite. And I took that result and I divided my results with it. And that gave me new values, C3. And so as you can see now, if I project those results in green on this graph, as you can see, the curve is almost aligned with the results of the integral. Again, it's not the same, but it's better than before. And even though it's better than before, I'm not happy with those results. I'm not happy with those results because it means that my formula becomes now something like this, okay? So it's my old formula divided by the calculated error margin. And honestly, this is not something beautiful to see, okay? I don't know what kind of spaghetti is this. It's not something really nice to present, number one. And number two, I have no explanation about to calculate the error margin. I just found the graph. I remember the graph. I took a similar graph and I tried to find a function that gives me almost the projected numbers of the error margin. But still, I mean, it's not really a demonstration. It's just like how I did, but it's not a demonstration. So this is why I'm not happy about this, and this is why I did not want to share this with you at the beginning, okay? But you asked me to give you some analysis, some of my work, so here is it, okay? So this is what I did so far. And if you want to know what's the error margin now with this formula, well, here is it. The error margin is, as you can see, very wavy based on the ratio of B to A. It's not linear. It's not linear. But at least the error margin is really small, okay? So here we are talking about a peak of 0.523, maximum 0.523%, and this is reached at a value of B over A approximately 0.77. So that's all. So I hope that you have enjoyed this video. If you would like to see more about my work on the ellipse, I invite you to go directly on my website. The link will appear either here above or below. I don't know. We'll see where I'm going to place this after the video. And basically on my website, you'll be able to see all the details that I published regarding this formula. I'm even explaining how to obtain the same circumference with adjusting the semi-minor axis and the semi-major axis. Also, I'm explaining why when you rotate an ellipse, you cannot obtain a flat ellipse, okay? So I use the flat ellipse, excuse me, I'm using the flat ellipse as a concept just for my demonstration, but indeed an ellipse cannot be flat, so you cannot have the semi-minor axis equal to 0. It's a limit. And that's all. So yeah, I invite you to go directly on my website and to see all my work in detail. And of course, if I make something new, I will not hesitate to share it with you. So thank you very much for your interest in my work, and I see you next time in another video. Bye.